I decided to go with a bit more of a general topic today. And also, for those who don't know me, my name's Sherrod. I'm one of the data scientists on the team. Um, I'm working remotely right now. I'll be out in the office in about 2 weeks, actually, for the all hands meeting. So hopefully, I'll get to meet you all then. Uh, but yeah, so either way, I decided to go with kind of a more high level topic today. There were a few papers I'd been considering, and they were all kind of roughly based on graph networks. And then I realized I needed to give a bit of a primer on graph networks. I don't know how many people are familiar with them or have been exposed to them yet. They're still relatively new to me as well. I haven't really started using until this year. And so I was writing a lot of background slides and realized I was going to run over time. And so I figured I'd just go with kind of more intro overview of the idea of graph networks, some examples of papers, maybe a flavor of them. And if there is interest, we can always dive deeper into them in a later talk. So this might be a little bit shorter than I initially wanted to be, but feel free to interject with questions or thoughts or anything like that throughout the topic. Um, so yeah, at a high level then, what is a graph? And so a graph you can think about really more generally. It's not necessarily a graph like you think about plotting X versus Y back in the day in school. A graph is a much more general mathematical concept where you're just basically saying there's a set of nodes that represent something and edges that connect those nodes together in some way. And again, those nodes can represent really any top or any type of thing. We'll talk about some examples on the next slide. And those edges then that are connecting those nodes, they can either be directed in saying that, A is connected to B, or here in this example, A is connected to C, but C is not connected to A. They can do undirected or kind of bidirectional in the sense that they're both connected to each other. A node can be connected to itself. So really, again, this is a very general framework where we have nodes and we have edges connecting those nodes. And then the nice thing with the graph networks is the nodes and the edges can actually have underlying features as well too. And so those features can be some sort of characteristic or descriptor about those nodes and edges. And that allows us to create these really kind of rich, robust representations of the data set that we're interested in. And so to define these graphs, really actually is just a set of matrices. So, we can draw the nice picture there like we have, or we could just go with the matrix representation that we have here. And so the two matrices that you kind of really need are the node feature matrix. And so again, that's the features, the characteristics of the nodes themselves, and then the adjacency matrix, which will basically tell you what's connected to what. There is also, again, potentially the edge feature matrix. It's a little less common because that really kind of is, think about cases like maybe if your graph represented molecules, then some characteristics about the types of bonds between the atoms in those molecules, that could be represented in the edge feature matrix. But again, it's not as common to have that. And so just to kind of give an explanation of what you're seeing here, so these are rough ideas of what relevant adjacency matrices or relevant adjacency matrix A could be for this graph, as well as the node feature matrix. And so here you can see that, for example, the first row here will say represents node A. And that basically tells us that node A is connected to itself, right? It has this self loop here. Node A is also connected to node B. So there's a directional arrow going that way. And it's connected to node C. So it has a 1 for each of those entries. Similarly, then, for something like B, it only has a connection to A, but it doesn't have a self loop and it doesn't have any connection to C. So again, this is how we can just define this whole graph in just kind of this nice two-dimensional matrix representation. And then the feature matrix really just needs to have as many rows as you have nodes in your data set or in your graph. And then the number of features can be as many features as you have, right? So here I think I said maybe the size would be the first column, right? The first feature. I don't know, maybe it was the color or maybe the edge density or something like that. But basically, you can just have all these different descriptors that maybe describe something about the graph directly or describe, again, your underlying features, which is really what it's going to be doing about the nodes themselves. And so, yeah, kind of been hinting at this, but basically we can use graphs to represent a lot of things. So we can talk about graphs in the context of images. So here I'm saying basically this 3x3 grid here, let's say that's a picture, right? Each one of those squares represents a pixel. That pixel has some sort of RGB value, let's say, or really any other wavelength you want to talk about. It can have any number of channels. And we can represent that as a graph. We could just say that every adjacent node, it has a connection, right? A bidirectional connection, right? This top left node is connected to the node to the right of it and to the bottom of it. You could even, I guess, say you could have a diagonal one going across here, but really you can just define it here as this square of, fully connected points within that square. And then the node features in this sense would be our RGB values for that exact pixel, or your, values for the different wavelengths. And then here again, like I said before, this one doesn't have edge features. So there's no real reason to define what or some sort of characteristic about the connection between these two. We can also talk about text being graphs, and this is actually one of the really common ways to see this. In this case, you could say maybe the words or the tokens for each of the words, those are the nodes. And then the edges connecting those are going to be maybe the ordering in which they appear, right? The dog ate the treat. And so we could connect the to dog and dog to ate and ate to the and so on. We could also say that everything within a sentence is connected to each other, or everything within a story is connected to each other. Or we could define some really like arbitrary, almost syntactic tree that says, well, this, relates to this in this way, and these are all part of one core concept, or this is a clause and this is a clause. And so you can do all kinds of really, interesting representations by defining this in kind of a graph structure. And then also more generally speaking, we can really define, again, like I said, almost anything. So you'll see it oftentimes talk about like friend networks or LinkedIn connection networks. Those can be represented and are represented as graphs a lot of times in the back end. So, companies like Facebook and LinkedIn do a lot of work in graph network development and learning and research, really. Chemical interactions, like we talked about, you could do the solar system. You could say planets are nodes, and the characteristics, the size, the mass, the color of the planets, the makeup could be the node features, and then the connections between those two, or between planets, would be the edges. And you could even then have edge features, like the gravitational attraction between two bodies could define an edge feature. So again, a really rich representational structure is allowed with graphs. And so that really gets to the question then of, if we have graphs, we probably want to perform some set of tasks on those, right? We want to either maybe predict new nodes, or label a node in a graph, or predict where an edge might exist in the graph. Or you could even just be trying to classify the graph completely, right? Trying to say, well, this graph represents this person's network, this graph represents this person's network. And so we have to figure out some way to kind of learn on those graphs. And neural nets obviously have been kind of like the go-to method for when you have really arbitrary structures like this, right? We have a lot of success using this on images, or neural nets on images and text, and these other kind of, I would say, less nicely defined data sets, right? It's not a nice rectangular data set where you can just, feed in any sort of learning method. And so we can think about then, what does it mean to pass a graph through a neural network? And so the simplest way, and kind of the first way this was thought of, is say, well, let's just use our standard feed forward, or multi-layer perceptron neural nets, and just pass in the adjacency matrix. That basically defines all the connections in the graph. Here I just said, okay, well, we can just take each one of these entries in the adjacency matrix, and that is just going to be a different input feature in my fully connected network here. And then I can define any number of hidden layers and so on, and maybe make some final prediction, whatever that final prediction may be. And conceivably that could work in some instances, but it does come with a few constraints that really make it limiting as far as a general purpose method for any type of graph structure. And so the first problem is really that the nodes are kind of being forced into a fixed structure, or to a fixed ordering. So you can see here, we said this is row A, this is row B, and this is row C of the adjacency matrix. But really, there's no reason to call this A, B, and C. We could have put this row up here, this row down here. It wouldn't have actually changed the structure of the graph. It would have just changed the ordering of the rows in the matrix. But in the context of a neural net, if this is the graph for, maybe this network, or for this, set of relationships, and then we get another graph that we want to pass into this neural net, the ordering that we put these nodes in is actually going to influence the way the model goes about learning. And so we can see it's kind of not able to adapt to an arbitrary ordering of the structure. Also, it assumes that these graphs aren't going to change in size. So here we have 3 nodes, which means we have, a 3x3 adjacency matrix. And that means that we have 9 inputs to our neural net. But now if I have a 4th node, there's really nowhere to put those extra connections that we would expect to have in there. And so you don't have a way to kind of naturally adapt to a new graph size, either during training or testing, right? So it hurts us in both phases of there. And then also, we're kind of ignoring these extra node or edge features. So here we said, well, maybe the color of the nodes or what that node represents, with the height of the person, their career path, whatever it may be of the graph representation, we can't put those features into this graph naturally. We would have to have some sort of weird large structure that gets added to this, or a separate module almost, right? It's just not a general enough architecture to be able to handle really any type of, or any edge or node features that we have to add on to this. So that brought us then to the idea of, okay, well, let's use something like convolutional neural nets. We know that they work well on images. Images are, like we've shown before, they really can be represented as graphs. So it's not a bad thought necessarily. But again, we run into this issue of images have a completely rigid size and structure. And actually the convolutional neural nets that operate on them are expecting a fixed structure or fixed size of image. Even if you have, a data set that has all different varying sizes of images, there's still gonna have to be some point in there where all images are transformed somehow to the same size, whether that means padding them or cropping them or, expanding them, shrinking them. We still have to get them into some sort of fixed structure for at least standard CNNs to work on them. And the way a CNNs works is we're just basically taking some sort of kernel. In the case of a CNN, we're going to learn these kernels and we're going to pass them over the image. So basically you take these 4 blocks, they would cover this top left-hand corner here. You'd multiply those together, you'd sum them up, and that would give you a new representation for this feature map in this position. And then you'd slide it across some stride amount, and then you get another representation, and so on and so forth. So basically, you're moving across this graph in a fixed structure, assuming that every connection exists between these in that square that we've defined before. But again, when we talk about an arbitrary graph, we could take these exact same values representing the node features here, and we could just start breaking connections, and it still would be an appropriate graph, right? This is still a graph. There are some connections that are directed, some are undirected. We've added some new diagonal connections. We've just deleted some. And so while this is still a graph, it still has the same node features, the same number of nodes. The act of passing this kernel over the graph really doesn't even make physical sense anymore, right? There's no way to perform this multiplication appropriately and remove this connection here or make this one connection here unidirectional. Just the structure itself doesn't really work. And so we really need to have something, that kind of meets all our criteria of, being first permutation invariant. So we can reorder the columns or the rows and columns in any way in our adjacency matrix and it won't affect it. We have to be able to adapt to not only arbitrary graph sizes, but again, arbitrary graph structures during training and then our inferencing step. And then also hopefully not make this too computationally inefficient. There's always going to be some inefficiency associated with making it more general, but hopefully we won't have too much of a cost there. And again, any questions at any time, I'm happy to stop and talk about them. And so that kind of brought about this this idea of neural message passing, or really the graph neural network. The idea here is that we can think about every node, or really the representation of the representation of that node. It should be some sort of aggregation of information from its local neighborhood. So again, here, for example, if our target node is node A, we might have some initial. Oh, go ahead.
Oh, can you hear us on this end?
Yeah, I can hear you.
Okay, yeah, I just had a quick question. Not even sure if it makes much sense, but in that last slide where you had the kernel, is there some notion of dimensionality in the application of the kernel, or is the graph still sort of abstract in terms of like geometric dimensions? Is it like a 2-dimensional thing? Does that imply 2 dimensions, or?
So this kernel, as I've shown here, is technically a 2-dimensional kernel, and assuming a fixed size, to some extent, 2-dimensional image. If we're operating on like an RGB image, then technically your kernel would be 3 dimensions, right? Because you'd have 3 channels and to the X and Y dimension still of the image. So there is an assumed fixed structure initially, if that answers your question. But really the point being that that fixed structure, or really the geometry of those, is not known on the outset for a graph.
Okay. Thank you.
Yeah. Any other thoughts before I go on? Okay. So yeah, like I was saying, what was that? Are you good? Okay. So as I was saying, they have, or we're interested in really understanding or creating an appropriate representation of each node in the context of its local neighborhood if we're trying to perform, some downstream tasks. So again, our downstream tasks might be, well, predicting some characteristic about a node, right? Maybe I want to know what a label is, an appropriate label is for node A amongst some labels. And maybe that's trying to predict, for example, in the context of, hiring candidates, I want to know if node A is going to be a good candidate or not. And I know information about B, C, E, F, and D. And so now I want to use that to try to predict something about node A. Or maybe I know that this graph represents a single person's network, and I want to know, basically predict, given their network, are they likely to be a good candidate for us, right? And so again, I need to somehow aggregate information into each node to create appropriate representations of those nodes themselves. And so the way this is done is actually really similar to what we do in neural nets and even convolutional neural nets to some extent, in that we know the local neighborhood is probably the most important information for a specific target node. And so what we'll do is we'll take all the nearby nodes, so let's say B, C, and D, those are the ones that are connected to node A. We'll aggregate information about them in some way or another. We'll just keep a generic aggregate function here. And that should then influence the new representation we have of node A. And then that'll happen at each node at the same time, really. So B is getting aggregated information from A and C. C is getting from A, B, E, and F. You can see C is connected to all those. And similarly with D, it's connected to A, and so it should get information from A. And so if you notice, what's happening really is that as we repeat this process, B is going to aggregate information from its neighbors, which is going to allow A to then aggregate information from the neighbors of B. So kind of we're over time expanding the the aggregation operation to reach the furthest reaches of the network. So even though in the first step, node A might only see B, C, and D, after the second step, it actually should also see information from E and F, because that's been passed through C, which will then get passed on to A in that second step. So that's the idea, is really we just want to have kind of message passing going on in this iterative fashion to learn new representations of the node. And so mathematically defined there, kind of the initial representation was defining these hidden representations of a node U at step K, so at iteration K. They define this by basically saying, we're taking some activation function, as we always do with neural nets. So this is just going to be some sort of squashing function, basically. It's going to squash between 0 and 1, or whatever your activation function is, not really important. And then the representation is going to be defined by some sort of weight matrix, again, a learned weight matrix, multiplied by the previous representation of the node itself, right? So this is this idea of, I shouldn't only aggregate information from my neighbors, but I should also probably take into account what I looked like before. And so it's going to take information from a prior time step, k minus 1, and then add to that a weighted sum where, again, these weights are learned, but these weights are with regard to the neighbors now, a weighted sum of all the neighbor representations from that prior time step. And so this is that idea of, again, we're going to take what I looked like before, what my neighbors looked like before, get a weighted sum of the neighbors, add that onto the representation I initially had, and plus some bias term, just an offset really. And that's going to create my new representation at this time step. And so then again, this is going to be an iterative process. So as we train over time, we'll just basically reach further and further reaches, because it's just going to be continuous weighted sums of your immediate neighborhood, right? And so this script n here is just defining the nodes V in the neighborhood of U, where U is basically our target node, and V is going to be all the other source nodes. Okay, that was a lot of talking too. So again, feel free to ask any questions. And so that kind of brought up, one issue. If you, look at this representation we had of that message passing operation, this is just, again, a weighted sum, which means that if we look at this graph again here, D only has one neighbor. So the weighted sum of its neighbor is just by just the construction of it going to be a smaller weighted sum than this one, which has four neighbors, right? C has four neighbors, D only has one neighbor. And so that's going to mean that these nodes with high degree, right, with a lot of neighbors are going to have a lot more or kind of an outsized influence potentially in the learning, which we don't want. There's no reason to say that just because it has a lot of connections, it's going to be important. For that matter, it might be that because it has a lot of connections, it's useless. If we think about something like if we have a graph that represents all the words in, some novel, the word the probably appears in more sentences than anything else. So it'll have a ton of connections to the word the from a ton of other words. But in most NLP tasks, we're going to toss out the word the as a stop word, right? It's typically not that important or critical in the understanding of the sentence. And so even though it has a high degree, it actually doesn't have a huge amount of importance. And so we want to be able to kind of bring that down and normalize it so that way that neighborhood aggregation is going to be kind of comparable across all the different nodes. And so the simplest way to do that would be just to take an average, right? Just get basically the number of neighbors, right? This is the neighborhood of U again, the size of that, how many neighbors we have, just divide that message passing operation like we had before by the neighborhood of U. And so that'll again average that out. And so that way it'll always just be in the context of itself, or really it'll be comparable across different nodes because they'll be normalized by the number of connections they have. And then graph convolutional networks came across, I think, 2016, 2017. And really their main difference there is that they're taking a kind of symmetric normalization term here. We're just doing the inverse square root of basically the target node's immediate neighborhood as well as the source node's immediate neighborhood. So it's trying to balance that, that how many nodes does the node that's passing information to me have, and how many neighbors do I have, kind of thing. So again, it's just a couple different ways to go about normalizing this representation across in the neighborhood of the node of interest. And then graph attention networks basically just take that a step further. So really, the important thing here is that this framework hasn't changed. All those different approaches and really all those different papers, even including the graph attention network, really still take this general format where there is some sort of aggregate function. And in the context of the graph attention network, the aggregate function is really just performing or basically treating it as almost a fully connected graph. But then you have these attention weights that you can learn. And so what we mean by attention weights is that, let's say that again, our target node here is this H1, and it's connected to 2, 3, 4, 5, and 6. And I want to form this H'1. And so what I'm going to do is I'm going to basically say that, okay, it's connected to each of those, and I should learn how important each of those nodes are in the understanding of this node, but only in the context of learning the representation of this node. So you can see that these attention weights, these alphas, they have, a subscript of 1, 2, which implies the connection between 1 and 2, and this one between 1 and 3, and 1 and 4, and 1 and 5, 1 and 6. And so then similarly, you would have a weight that is H6, 1, which will be the connection from 6 to 1, or vice versa. So you're basically creating more connections, or really more importantly, you can take the existing connections as you have already, because if you know that maybe, for example, in this case, 6 shouldn't be connected here, you can just ignore that weight. But really, you're taking the existing connections you have there and trying to learn individualized weights for each of the connections. And then conceivably, you could really take that a step further and do kind of what we do in transformers and just have multi-headed attention, which just says, okay, well, don't just learn one weight for 1 to 6, learn a ton of different weights, right? Learn K different weights from 1 to 6, randomly initialized differently, so that way they could conceivably come to different representations. And then we'll just concatenate or average or somehow aggregate that information again in this final step, and that'll form this new representation. So this has kind of, again, been the success that transformers have had by allowing for so many different, or providing so many different ways to represent the data. You can create these richer representations at the cost of increased computational complexity because you have a ton more weights now, right? So again, I won't dive too deep into the actual like calculation of this, but at a high level, the attention weights are just going to be kind of this, nice, typical softmax operation, um, where we're looking at again our target node, which is that H sub u, and our source node is H nu. There's a couple different ways to perform this calculation. This is just one of them, where you basically learn, or you have a neural net layer, at least one layer in there that learns the representation there. And then again, you're aggregating that amongst this local neighborhood, just as we've done before. And then this is just, again, the multi-head attention part of it. And so to take the brief detour to transformers, because we've kind of been hinting at it a couple times, this is on the left-hand side, just the original visualization of what the transformer looks like from the attention is all you need paper. And then I just kind of blew that up to dig into, like, at a high level, what's happening in that phase there. Really, this is the phase of interest, right? This is where most of the transformerness exists, in that we have some input embeddings. We add on to it some positional encoding, right? That's just to encode where an embedding appears in relation to the other ones. If we're thinking of it in the context of a word or a sentence where we have words as our inputs, then we would encode basically where that word falls in the sentence. But basically, that's going to get passed on then to this first multi-head attention layer. And the purpose of that in the transformer is that we want to learn an appropriate representation of this word or of any of the words in the context of all the other words in the sentence. So you can see here that the input to this first block, or this multi-head attention point, is not just the node or not just the word at this point, but it's also all of the other words that are in the sequence. And then we're going to learn how important basically each of these lines are, each of these connections are in the understanding of this embedding. And so we'll perform that whole process in all these multi-head attention layers, and that'll form some new updated embedding for the original input. And so we'll have as many updated embeddings as we have input embeddings. And so again, this is effectively how the transformer works. It then goes through a couple more steps, but really that is the crux of it, right? This is a transformer layer. And looking at this, it was kind of drawn in a way to try to illustrate that this is a graph. By definition, or by construction, really, a standard transformer layer is exactly a graph attention layer, if that graph attention layer is using multi-headed attention with a fully connected graph. And so to kind of illustrate that, if we think again back to that sentence I showed before, the dog ate the treat. If we represent that by a graph where the words are only connected sequentially in one direction, that's actually pretty similar to a recurrent neural network, right? Where at the first time step, we're going to take into account any initial embeddings, but really, or actually let's talk about the second time step because it's a little clearer. But to form the output at the second time step, we're going to take what the previous time steps output was. You could either take it from up here or maybe the previous representation, and then also the current time step, and that's going to form a new representation, and then that process will repeat. And so again, this is all just connected in one direction. The transformer then basically added so much power, improved so much, basically because it just added a ton more connections. Everything was connected to everything, right? It's kind of a fully connected layer on steroids to some extent. So everything's connected to everything. And now we're learning the importance of each word and the understanding of each word. And so it's kind of like having a fully connected graph where every word is connected to every word. But now if we talk about the graph neural network, or specifically a graph attention network, this is actually the same thing. It's just a more general format of the transformer, in that we can break some of these connections. We can remove them entirely. We can make them unidirectional and just say that we're only calculated an attention weight for one direction of the connection. And so really that's the kind of interesting thing about this, is we can kind of recover the transformer if we want to from a graph attention network layer. But we have the flexibility to do a lot more interesting things, and that can have a lot of benefits that I'll talk about here in a second. And so let me see how I'm doing on time. Okay, we're good still. So yeah, go for it.
A quick question on this slide. Like your statement at the bottom, I guess there's like a little asterisk of standard transform layers, blah blah blah, plus the positional encoding, right?
Yeah.
And
Yeah.
like, is there like suppose suppose instead of like making a transformer layer like a GAT, like the other way of like if you have a graph, like can you like if you make that graph fully connected and then somehow the connection like is there could you do like a positional encoding for
Yeah.
you know what I'm saying?
Yeah. Yeah. And
I think anyone else does because I'm like stammering, but like
no, so the reason I get it is there is a paper doing exactly that. That was almost one of the ones I talked about. I just wanted to kind of give more of a background to it, but I'm fairly certain there's a paper that's it's called Graph Transformer or something along the lines of that. If you just Google Graph Transformer, you'll get it right away. But it's basically trying to do exactly that: replicate the transformer's structure in a graph defined environment, if that makes sense, right? I mean, you're still like you're going to be doing the same operations, but you can do that because it is exactly that, right? I just take my graph then and say that, okay, even though it, or like if we imagine that one on the right hand side there, we can just make all those connections exist and then add to each of those input word embeddings the positional encoding exactly as they define it in transformers. I mean, I think in the paper they proposed an alternate positional encoding. I forget how they defined it, but either way, they add on a positional encoding exactly the same way and proceed through the process. So there's really no constraint. You can go back and forth between them. That's a true statement, a fair statement.
gotcha. All right, thanks.
Yeah.
I have a quick question too, Sharad, and
Yeah.
it could have gone back a couple of slides, but it's carried through to this one, so we can stay. Like, how does the directionality on the edges come into play here?
Yeah. So really in the context,
Because even in the neighborhood definition, you need like left or right neighborhoods, or you just assume they're all symmetric.
yeah. So in the context of calculating the transformer, like if we wanted to assume there was directionality in it, wish I had a different slide up here now. I should have brought one of these other ones up. But either way, when we're doing the actual self-attention calculation in the transformer, you're basically taking, if we imagine just for one word, so the first word the, we would have some word embedding for the. We'd multiply that word embedding by a weight matrix, a query weight matrix that would form some query vector. And then that query vector would be multiplied by a bunch of key vectors that are created by doing kind of the same process, but multiplying by a separate matrix. And so what you're going to have is you're going to take that input word the and multiply it by the key vector for the word the, and that'll give you self-attention or a self-attention score to some extent for the word the. How important is the word the for understanding the? You do that same thing then and say multiply the query matrix or query vector for the by the query vector or by the key vector for dog, and that'll give you how important dog is in the understanding of the. And so you kind of repeat that process. And so the directionality to some extent will come in that, well, if the isn't connected to treat, as we can see here in this right-hand graph, if it's not connected to that, then you basically just wouldn't do that last calculation, or you'd do something.
But that's whether it's there or not. I meant like you've got an arrow from V to 8.
Yeah.
Or from treat to 8, but you don't have one from 8 to treat.
Yeah. And so that's basically when you get to, because you're going to repeat that query key multiplication for each of the words separately. So then you're going to, once you get to the word 8, when you go through that query key multiplication, you're going to multiply the vector for 8 by the vector for, let me see which one's connected. Oh, it's not connected to any other ones. But you'd multiply by any of the ones it's connected to. But then if you got to treat, since there isn't a connection in that direction, you basically would just ignore that calculation. So you wouldn't be getting how important treat is into the understanding of 8. Basically, you wouldn't be aggregating information from treat to create a new representation of 8. That's basically the idea of what you're doing there.
Okay.
Does that make sense? It's really hand wavy, and I apologize for that.
Okay.
Yeah, but that's the idea is basically that you can drop out some of those calculations. And that's really arguably the motivation of doing something like this from a graph standpoint versus a transformer standpoint, is that the way I've kind of interpreted it for personal usage, at least, is if I have a kind of expert understanding or expert knowledge going in, or some domain expertise that says these two things shouldn't be connected, then I can kind of ignore that calculation, save the computation, and potentially improve performance, especially in a data constrained environment, which was kind of me segueing myself into applications. So this is an example of something I'm working on kind of actively right now on a separate project, kind of outside of Striveworks. but it's piggybacking from some work I did last year with some people in a speech language pathology department out here at Utah State. And what they're trying to do is predict, basically, they have a rubric for scoring children's narratives. And so they'll elicit narratives from kids, and then they'll go through and they'll say, okay, well, from a scale of 0 to 3, how do they perform on character development? Or how do they perform on defining and initiating events and concluding that initiating event appropriately? And so they have all these kind of somewhat subjective descriptors there of things they need to score. And it's obviously very difficult to score. It's very time consuming. And the real critical piece of this is that they do this at schools. And so this is kind of supposed to be an ongoing, kind of intervention style treatment where they can give them some sort of test, give them some sort of education knowledge, and then test them again and see if these different scores have improved. And so one difficulty they have, though, is because it's so subjective in how you score this, it's really difficult for this kind of progress monitoring aspect of it. And so we've been working on, to some extent, trying to automate the scoring of this, which obviously it's a narrative, it's a big, long text, and we want to perform some sort of regression classification type of task on it. And so the gut feeling there is to go through with the transformer and hit it with a hammer and, go home and take your win. But unfortunately, we really have kind of a constrained data environment in that obviously there's not a ton of these narratives. They can vary wildly in their lengths from, barely a sentence to, dozens of sentences and paragraphs. And so the transformer has really been struggling with that, not only from the, again, computational side of things, but also in the way a lot of these transformers are pre-trained. We don't have near enough data to train them from the ground up. And so we have to kind of use these pre-trained models. But almost exclusively, right? If we think of all the OpenAI GPT models, those are doing next word prediction. Their goal is to really do a kind of a generative text modeling task. And they're pretty solid at that. They're not necessarily open to everybody to use, but they're decent at generative text. Something like BERT has shown a lot of success in things like question answering and, a variety of other tasks associated with, word representations in general. And they do that masked language modeling. So they're trying to predict masked words within a sentence. And then also I think they do next sentence prediction as well, right? Do two sentences match each other? And so maybe BERT's trying to get at a bit more contextual or semantic understanding, but it's not really hitting the nail on the head with that one. They're really kind of doing this low level, word level prediction. And that has been shown. I mean, that's really what we ran into is performing really poorly on these more complex narrative type tasks, narrative prediction type tasks. And so I haven't had a ton of success with this yet, but this is kind of the approach I've been going down, is now saying, well, if I switch to a graph network, can I basically reduce the number of connections to make this a little bit more feasible to train on our constrained data set? And the nice thing about that is, from a graph standpoint, we have a lot of tools to construct graphs on text that have gone back for many decades, right? And so on the right-hand side there, the top right, I'm just showing an example here of a syntactic tree versus a semantic tree. So we can do something like this, right? We can do part of speech tagging, or we can do some of these more semantic trees. This is a bit more difficult, not necessarily an automatic task, but you can do these things where you basically construct different types of graphs that relate words in a completely unique way to basically just doing a fully connected graph. And that'll hopefully kind of that bias going into it might give us a chance to get some at least initial improvements in performance while saving on the computational complexity associated with it. So we're just trying to, again, exploit some of the domain expertise that's been established through linguistics by using existing graph structures that they already have and they use fairly regularly. I mean, a lot of these far predate neural nets. So that's kind of one path we've been going down recently, in a place that I've found graphs to be somewhat at least interesting and potentially better as an approach to using transformers, at least in an NLP context. So yeah, this is the last one I'll show here. This paper came out very recently. It's a paper out of Google. Basically, at a high level, what they were doing is they were designing their new, or they claimed their next generation TPU. It wasn't clear if it's the TPU v4 that was just announced at I/O, or if it's an upcoming generation. but they are saying they are training or creating their next generation of TPU chips using this approach where they define the chip itself as a graph with nodes as these various chip components, adjacency matrix being connections between them. But then they actually use it in a reinforcement learning environment. So they use the graph to form the representation, and then that representation is passed on to their policy and value networks as you would have in a reinforcement learning framework. And basically then they define the states as the graph, right? That current chip configuration. The actions are then there. Where should I place the next chip components? They kind of do it as a sequential problem. There's an argument to be made if it should be sequential or if you can do it kind of as an all-in-one optimization, but they did sequential. And so actions are, where is the next component placed? And then they just find their reward as 0 for everything, all actions except that last one, where they have some, weighted sum of the wire length, congestion, density, and some other things in there. But really, they just, again, are using this graph now as a nice abstract way to represent the chip, as opposed to, let's say, I honestly don't even know how you come about it without a graph representation, because, again, you could represent the chip components as individual features. But again, it is this relationship between them, right? It is, because you can see the wire length, congestion, density, those are all based off of these spatial relationships. And so by defining it as a graph structure, you can really naturally represent what is important for your reinforcement learning agent to actually learn. And that's kind of the most critical part of reinforcement learning, right? Is having the appropriate representation to have effectively a fully observable system to train on, right? If you have some sort of hidden features, or if it's, kind of an abstract representation, then that's going to make that reinforcement learning step very difficult. And so this was a really interesting paper. And this was actually the one I wanted to talk about originally, but I felt there was too much background. I already ran pretty long, so there's too much background to get into to, dig into this too deeply. But again, highly recommend looking at it. It was just published in Nature, I think, and they have somewhat of a blog post about it. But yeah, pretty interesting application of both reinforcement learning and graphs. So highly recommend it.